You tap a button on an app. It feels instant, right? But in that split second, what really happens? We're about to go on a journey. We're going to follow one single user request from the moment it leaves your screen all the way through the guts of a modern backend system and back again. Let's get started. So here's our game plan, the 5 main stops on our trip. We'll start at the system's front door. Then we'll see how all the different parts of the system chat with each other. After that, we'll tackle security. How do we know who's who? Then we'll look at a really modern problem, connecting to AI. And finally, we'll see what it takes to keep this whole thing from falling apart. This is the stuff every engineer has to know. All right, let's meet our hero. A single request is just a little packet of data, born from your finger tapping on glass. It's a simple instruction, show me this photo or add this to my cart. But the real question is, how does that one little tap unleash this whole cascade of complex events inside a giant distributed system? Let's follow the breadcrumbs. Okay, first stop, the front door. Every single request from the outside world, whether it's from a web browser or a mobile app, has to come through this single point of entry. This is our system's welcome mat, but it's also its first big test. And that test is all about scale. We're not talking about one person showing up. We're talking about millions of requests all banging on the door at the exact same time. If they all rush one server, it's going to get trampled and fall over, guaranteed. So how do we manage that chaos and keep the lights on? Well, we've got 2 main tools for the job. Over on the left, you have the load balancer. The best way to think of this is a simple traffic cop. Its only job is to see a line of cars coming and direct them into different lanes, so nobody gets stuck in a jam. Super effective. But on the right, you have the API gateway. This is way more than a traffic cop. It's like a bouncer and a receptionist rolled into one. It doesn't just direct you, it first checks your ID, asks what your business is, and makes sure you're allowed to be here before it even lets you inside. Okay, and this table? This is pure gold for a system design interview because it's all about the trade-offs. You can see the load balancer is simpler. Its job is just traffic distribution. An API gateway, though, it's more complex. But look at all the extra stuff it does for us. Authentication, routing, caching, all in one spot. So for a basic website, yeah, a load balancer is probably fine. But for a complex system with tons of little microservices, having that intelligence at the front door is an absolute game changer. So for the system we're building in our story today, the API gateway is the clear winner. Why? Because our app isn't one big program. It's a bunch of small, independent microservices. The gateway gives us one smart, central place to manage the chaos, which makes everything else that follows way, way simpler. So our request made it past the bouncer. It's inside the building, but to actually get anything done, it can't just talk to one person. It needs to coordinate with a bunch of different departments, or in our case, services. And to do that, they all have to be speaking the same language. And this leads us to the next big headache. Inside our system, we might have a service for users, one for products, another for payments. You get the idea. They constantly need to talk to each other. How do they do that without it being slow and messy? The choice we make here is going to have a huge impact on how fast our whole system feels. We've got 2 main dialects they can speak. On the left is REST. Think of this like sending a formal letter. It uses the standard postal service of the internet, HTTP. Everyone knows how to read it, and it's very reliable. On the right, we've got gRPC. This isn't a letter, this is a high-speed direct phone call. It uses a super efficient compressed language, and it's all about raw performance. And this table perfectly captures that classic trade-off, simplicity versus speed. REST is easy to use, it's human-readable, and any web browser can speak it, which makes it perfect for public APIs that talk to the outside world. But it's slower. The messages are bigger. gRPC is the opposite. It's a bit more work to set up, but it's incredibly fast and efficient, which makes it absolutely ideal for all that high-speed internal chatter between our own services. So here's the secret, and this is what real-world systems do. You don't have to choose just one. You use both. Our API gateway, the bouncer, talks to the outside world using friendly, understandable REST. But once a request is inside, all the internal services talk to each other using lightning-fast gRPC. It's truly the best of both worlds. Okay, our request is now moving smoothly around the system, talking to all the right services. But hang on a second, there's a huge security hole. We need to know who this request belongs to. It's time for a passport check. Just think about it for a second. The request goes from the gateway to the orders service, which then talks to the payment service. Each one of those services needs to know, is this person allowed to do this?
We can't keep asking the user to log in at every step. So how do we staple their identity to the request so it's trusted everywhere it goes?
Once again, two classic ways to solve this. The old school session-based way is like a coat check at a club. You give the server your coat, it stores it, and gives you a little ticket. Every time you need something, you show the ticket, and the server has to go look up its records to see who you are. The other way is with a JWT, or JSON Web Token. This is completely different. This is like getting a passport. Your photo, your name, your permissions, it's all right there in the passport, securely signed. Any service that knows how to read a passport can verify you on the spot, without asking anyone else. Now, the most critical difference, the one that really matters when you're building massive systems, is state. Sessions are stateful. The server has to remember you, and it usually does that in a central database. And as you get millions of users, that one database becomes a huge bottleneck. JWTs, on the other hand, are stateless. The server doesn't have to remember a thing. All the info is in the token itself, which makes scaling up a breeze. And that leads to this quote, which you should basically memorize for any system design interview. Statelessness is a superpower for scalability. By using JWTs, any one of our microservices can check a user's identity all by itself, without having to phone home to a central database. It's faster, it's more resilient, and it's just a much cleaner design for large systems. So our request is in, it's authenticated, and it's moving through the system. But let's say our user asks it to do something really clever, like summarize this 10-page document for me. Our normal services can't do that. They need to go consult a specialist, in this case, a powerful AI model. And this brings up a whole new set of challenges. To solve this, a really interesting idea is starting to gain traction, the Model Context Protocol, or MCP. The easiest way to think about it is as a universal translator and toolbox for AI models. It's a proposed standard that creates a common language, allowing any AI model to securely access any external tool, whether it's a simple calculator, a weather API, or a private company database. So why is this a big deal? Well, without a standard, every time you want an AI model to use a new tool, you have to build a custom, clunky integration from scratch. It's a total pain. A standard like MCP creates a true plug-and-play ecosystem. It means any model can securely find and use any tool that speaks the same language. This is a massive deal for building powerful and flexible AI applications. And there we have it. Our request has made it all the way through the system. It got past the bouncer, it spoke the right language, it showed its passport, and it even talked to an AI genius. But we all know that in the real world, things don't always go this smoothly. Things break. We need to talk about what happens then. And this is the final and maybe the most practical stop on our journey. A user gets an error message. Their request died somewhere deep inside our complex web of services. It's 2 o'clock in the morning, an alarm goes off. How on earth does an engineer figure out what just happened? This is the world of debugging and observability. Here's a quick look at the classic hands-on debugging flow using some fundamental tools. First, you SSH to get a secure shell connection right onto the machine you think is having trouble. Second, you use a powerful search command called grep to hunt through the log files for a unique trace ID that we attach to our request at the very beginning. This lets you see every service it touched. And finally, if you want to see what's happening right now, you can use tail-f to get a live, real-time stream of the logs. This is the nitty-gritty work of keeping a big system alive. So, we've traced one single request from start to finish. It was a synchronous journey. It asked a question, and it waited for an answer. But what happens when the system's job isn't to answer one question, but to process a continuous, nonstop fire hose of millions of events every second? Well, that requires a completely different kind of architecture, and that's a story for another time.